So good evening everyone. So today we will be mainly discussing upon week 7's content, which is mainly based on solution to linear algebraic equations. Now this is somewhat different from whatever topics are in general covered in computational fluid dynamics. So this tutorial is for the course ME75, which is in foundations of CFD. So that is why I told that this particular week the discussion is more general. I mean you can it's not restricted to computational fluid dynamics. You can apply it in other areas also. So in that sense, we are trying to see how we can solve any given set of linear equations, because in CFD we have seen from our week 1 to week 6 uh, that we mainly take the governing equations. That is what we had looked into in week 1, right? So we take the governing equations, we see what are the governing equations for fluid flow, what are the governing equations for uh, energy conservation, okay, and for temperature how we can come up with the governing equation using that energy conservation. So those things we had seen in week 1, and then mainly in week 2 we kind of saw, okay, how can we just write a simple df by dx in terms of neighboring grid points, okay, in terms of discrete values of f, how we can write df by dx. Okay, and when we do that we also land up with some error, discretization error, which is called as, okay, but we were trying to see mainly how we can write that derivative term in terms of the function values at discrete points. So that we were trying to see like in week 2. Okay, so these are a systematic way in which you kind of learn CFD. Okay, so then we mainly got introduced to finite difference method and the finite volume method for discretization, which are very commonly used for computational fluid dynamics. So the ultimate objective there was like we had governing equations with us. Okay, so we wanted to try to write it in a linear algebraic form. So that was the main objective. Otherwise, we cannot directly solve the governing equations in their partial differential format. Okay, so we came up with different strategies in finite difference method, whereas the finite volume method was a more of having a physical meaning with it. That we say that the conservation are equations are valid over a whole control volume, and we integrate the equations over the control volume to get discrete equations. Okay, so that was the main principle there. So that we studied in say week 3 and in week 4 also. Then we slowly moved on to how we can in particular solve our Navier-Stokes equation, which consists of the mass conservation and momentum conservation for fluid flow, if we are dealing only with fluid flow. But in between that, just before getting into Navier-Stokes equation, we also saw what are the different like time marching schemes which are employed in CFD. Like you have unsteady equations. So basically we have to go from one time level to the second time level. Okay, so how we can achieve that? So that was like a what do you say, a principal technique which will be needed later. So for while solving Navier-Stokes equation. So that understanding we got, and then slowly in week 6 and 7 we went into, sorry, in week 6, this is week 7, so in week 6 we mainly solve how we mainly saw how to solve the Navier-Stokes equations using the different algorithms. Okay, because there were many challenges when we saw Navier-Stokes equation. Like the pressure and velocity were coupled, and also the equations were highly non-linear. And then we saw that with a conventional grid system we run into pressure velocity decoupling problem. So we saw different techniques how we can overcome that, ultimately get some linear equations. Okay, that's the whole objective. Okay, so and we got introduced to turbulence also, how we model turbulence. Now this is all one aspect. Okay, now the second aspect, which is very important uh, at least in my opinion, is that you need to know how to optimally solve these equations. Okay, the term optimally has a very big meaning. Okay, it has a uh, very high importance, at least with respect to my perspective, what I have learned in my experience with CFD. Okay, so not only getting this linear algebraic equation is one big challenge. The second big challenge, which we will mainly try to see how we can solve it today, is how do we solve the linear equations. There are like many ways. Okay, so you need to select an appropriate way, a best way to solve this. If you don't do that, and if you go with very conventional approaches, you run with two problems. You end up with two problems. Okay, so one main problem which you will face is it will take a huge amount of time to solve those equations if you are going with a very rudimentary techniques, anyway, which we will discuss today. All the techniques we will discuss today. Okay, it will take a lot of computational time, especially for your Navier-Stokes equation. Okay, especially if the flow is varying too much and there is a very quick change in physics which is happening in the flow. Okay, so there the computational time will be very high if you are going with very basic techniques. Okay, the second problem which you will end up with is the convergence problem. Okay, so some of the equations kind of are very coupled, and we will see that when the equations are coupled, you will get too many elements in a matrix. It, usually what happens is that these when you solve Navier-Stokes equation, especially on a Cartesian grid, simple Cartesian grid, many of the elements in the matrix system, they will be zero. Okay, when we get linear algebraic equation, we try to bring them into Ax is equal to b, so that is what I am referring to as matrix system here. Okay, so there what will happen is that many of the elements will not be zero. Okay, for a very coupled kind of system, and there you will run into a convergence issue if you are using a very rudimentary solver and all. Okay, so these are the two problems which you will end up with. So that is why you need to assimilate this topic uh, with a very good importance. Okay, you have to understand this topic properly so that you can finally kind of complete the learning of CFT. It's like the last part, but that last part is very important. So this is a 8-week course, so this is just the last but 1 week. Okay, this is a penultimate week, but very important, I would say, and it is like a standalone part which you anyways learn in some other subjects also, which you might learn in like numerical methods for engineering, something like that, some course like that. But yeah, but here it plays a very important role. So that is what we will be trying to see here. How do we get the linear equations? In what format we can arrange them? And once we arrange them in a certain format, how can we solve them? What are the different strategies which we can apply to solve these linear algebraic equations? And very important, which method will be more suitable to what kind of equations. Okay, so that is what you have to understand. That is very important. Now you might feel that, okay, I have told this in the previous classes also. So whenever you start with a CFD, okay, just let me just share my screen. Is my screen visible? Okay, thank you. Okay, so whenever we start with CFD, I had told in the last classes also, in the previous classes also, that we have usually unsteady equations. So for example, if you just take a one-dimensional conduction, unsteady state conduction, okay, you have dou t by dou t is equal to alpha into dou square t by dou x square. we usually start with this format of equations, and we usually started with one standard set of methodology to solve this type of system of equations. And I told that since we are in the beginning stages of CFD, that would be more easy. That was mainly the explicit time marching. So what we did in that explicit time marching was, when we kind of discretize these equations, we directly wrote Tn plus 1 is equal to Tn plus alpha delta T into, what we did here is we wrote this discretization in terms of nth time step instead of writing it at n plus 1. So now this we called it as explicit time marching. Okay, now why we did that? As I told earlier also, this was very simple thing to do. Okay, especially with respect to coding. Okay, you could have directly found out T new using the T old, that is using the previous time steps temperature. Okay, so that was our main objective there. Okay, but as I told, when the problem becomes very difficult, these explicit time marching schemes are not very stable. Okay, and we usually have to go with the implicit time stepping schemes. Okay, there what we do is that there we calculate, apart from whatever is there in the temporal term, all the spatial derivatives and the spatial discretization that is performed at n plus 1 time level. Okay, so that's the main difference here. So we land up with equations something like this: minus 2t plus t n plus 1 n plus 1. This is at I plus 1, I and I minus 1. Okay, divided by delta x square. Now what you can clearly see here is that you cannot directly get the value of Tn plus 1, because Ti say at n plus 1, because on the right hand side also we have Tn plus 1, Ti at n plus 1, also we have Ti plus 1 at n plus 1. Okay, and we have Ti minus 1 at n plus 1. So we need to simultaneously solve these equations. Now we can rearrange them to get something like linear equations, like AP into Ti plus AE into Ti plus 1. Okay, AW into Ti minus 1, which you know is equal to some B. You can rearrange this equation. Now you have to solve them simultaneously uh, to obtain the equations for Ti's. Okay, so usually what we try to do in a typical CFD setup is that once we get this equation, we try to derive these equations on paper. Okay, so first we do that. Okay, we get this AP AEs. So then we try to form a matrix A. Okay, wherein, like for example, the first and the last grid point you have boundary conditions, so just ignore them. So for T I is equal to 2, you get what? You get AP and AE. Okay, AW you already know, AW into TW will be already knowing. So then all the remaining elements here you can clearly see that it will be 0. Now for the second, that is for the third element, I is equal to 3, you will get AW also, AP also, and AE also. This you will try to multiply with, say, T1, sorry, T2, T3 up to Tn minus 1. Okay, now you can clearly see that AP into T2, AE into T3 for I is equal to 2, that will be equal to B2. Okay, if I say again, there is a column matrix here, B1, B2, Bn minus 1. Okay, so then you can see that this, whatever equation I have written here, this will perfectly match with this matrix format. Okay, so I hope the matrix format is clear. If it is not clear, you can write down whatever doubts are there on the chat box. Okay, I'll be monitoring the chat box. Okay, yeah. So once we get this standard matrix notation, this is known as AX is equal to B now. Okay, Now we have to solve this equation. Now we have all learned in our elementary schooling and all that basically if we get such equation, then x will be equal to a inverse into b. That's the standard thing which we do, which we have done in our school also. Okay, so we directly calculated what is a inverse using that 1 by determinant of a into the transpose of that cofactor adjoint matrix. Okay, so that matrix we used to find first, and then we used to calculate a inverse. Once we calculate a inverse, we used to multiply it with the B matrix and then get X. Okay, but this is not viable in CFD. Actually, this type of solution is called as direct solution. I'll come to that at a later point. But you can understand that if I have, say, for example, even if I have five elements, okay, five grid points, okay, this thing to implement becomes very difficult. Okay, you will land up, okay, there are totally seven grid points actually. The first and last are boundary grid points, and there are five internal grid points. Now you will end up with a 5 cross 5 matrix. Okay, now for 3 cross 3 only, you know how difficult it will become to put all these elements, okay, here in the cofactor matrix and all. Okay, but when it is 5 cross 5, then how will you do that? In at least on pen and paper, it becomes with pen and paper it becomes very difficult. Okay, so now even computer can handle these things in a much more easier way. Okay, determinant can still be calculated by a computer. Okay, but once you get into a very large number of grid points, say for example in 2D cases, if you have say 200 cross 200 grid, okay, then it needs to solve as many as like this 200 into 200 kind of determinants it has to find out, and then the inverse it has to calculate. It takes a huge amount of time, and you can easily see that your workstation will get hanged up, okay, if you are trying to do these things. And actually in MATLAB also there is a limit. Actually, I don't know the exact limit, but if it crosses 1 million it just cannot solve it or something. Like if you multiply this, and if it the total number of these equations, the or size of this matrix, if it causes some limit, it cannot solve. Okay, so that's the whole problem here. So you cannot directly calculate this. And why do I need to do that anyway? So that is one point which I might have missed out. Yeah, I told, right, like it might be unstable and all. That is one point actually what I told. The other point is that, see, this delta t needs to be within the CFL criteria which you might have studied. Okay, so basically what happens is that the delta t is always restricted by the speed of wave propagation in an explicit time marching scheme. Okay, because we are calculating t at n plus 1th time level using all the values at t at nth level. Okay, so the solution wave has to sufficiently propagate properly. So if the wave propagation speed, if it is very fast, then the delta t should be very low. Otherwise what will happen is that, see, if you give a kind of pulse here, and delta t, if you select very high, delta t is equal to 0.01. Okay, now assume that if the velocity is very high at delta t is equal to 0.01, the wave kind of directly reaches into the middle of the domain, whereas still you are at the second grid point that delta t is equal to 0.01. Okay, now you try to calculate using the old values of this neighboring grid points, uh, whose values which you take in will not be physical. Okay, because in actual reality the wave is not there in this domain itself completely, it has gone out. Okay, that happens with pulse. Okay, so it becomes very unphysical to take very high delta t in an explicit time marching. So that is the second reason why you don't take explicit time marching. Okay, so that is why you have to go with implicit time marching in some cases. Okay, and then finally when you do that, you will end up with such troubles, okay, of solving this ax is equal to b system. The other place where you land up with the trouble is like, even if you are say solving an explicit time marching scheme, even then you find yourself to compelled to solve a Laplacian equation for it's not Laplacian, it's a Poisson equation for pressure. Okay, especially in Navier-Stokes equation, if you are, say for example, solving it using the projection method, which is quite famous and considered quite easy also. Okay, so there also, first you can try to predict u star and v star using the values of u and v, and p is not anywhere required. U star and v star can be predicted using un and vn. Okay. Now to correct this, you already know that we need pn plus 1. Okay. To correct the velocity, you need pn plus 1. So in projection method, what we typically do is we solve a pressure Poisson equation, like we solve delta del square Pn plus 1 is equal to rho by delta T of the mass flux which is remaining from this u star. Okay, if it was un plus 1 it would have been 0, but here it remains and this becomes a Poisson equation. Okay, now you have to solve this, right? Now again, if you have to solve this, you will again come up with this APAW format, and again you are stuck up with this AX is equal to B system, and you have to solve this. So that's the necessity of learning how to solve this. Okay, so in a sense, I hope that you have got an appreciation so in order to understand why we have to really solve this. Okay, so now that is one thing which I wanted to discuss before getting into the contents, why we have to kind of solve these equations really. Okay, so once you have kind of really understood, and the second step what it will be is to mainly understand what are the different techniques which are there, okay, to kind of solve these equations. Okay, so that's the whole content which was there for your week 2 actually. Okay, so that, just let me kind of summarize this content. Okay. So as I told earlier, when you have like a system like ax is equal to b, you can directly get x is equal to a inverse of b. So this is a direct method actually. It's called a matrix inverse method. It's a direct method. In one go you can get it. Okay. So these are called as direct methods. The direct, why they are called as direct methods is because you know a certain procedure which has to be done. Okay, you get a perfect solution, exact solution of this x for this x values. Okay, you get perfect solution, and you know that we have to, okay, follow this procedure, and that's a kind of more mathematically correct procedure which you do. Okay, now, apart from this direct inverse, which is not feasible as I told, there are many other methods also which you had gone through in this weekly content. So, like in the direct methods, what all methods did you have? You had mainly your Gauss elimination. Okay, that was the first thing I think which was learned, which you had learned in this content. Okay, so what do we do in that Gauss elimination? So we get a matrix, say A, B, C, D, okay, E, F, G, H, okay. Now what we try to do is, now similarly, uh, the whole matrix is filled like this. Okay, now we try to first check whether this matrix has a diagonal dominance or not. Okay, so that is also one thing which is very important. That is the this diagonal element, whatever is there, it should be greater than the sum of these elements. We try to check whether that is true or not. Okay, so if it is true, we can easily, what do you say, convert this matrix system in such a way that we finally land up with the matrix which has either a lower triangular or an upper triangular form. Okay, now if I say upper triangular form, so apart from this upper triangle in this square matrix, all, and one thing, we are dealing with square matrix here. Okay, so say for example I have in 2D, if I have n cross m grid points across x direction and across y direction, okay, you can clearly see that I will end up with a nm cross nm matrix. Okay, so this is a square matrix. The order will be nm cross nm. Okay, so this is a square matrix, and you know what is upper triangular matrix. So whatever elements are there in the upper direction of this diagonal, okay, those elements will be filled in with some values, whereas all the other elements they will be zero. Okay, so we try to bring the matrix into this format. That we do by using row manipulation, which you have learned in the class. Okay, so there is a step by step procedure also which is given. So first we try to make this element e0. Okay, so then we go to third row. Okay, then we try to make these two elements to 0. Okay, so that we only get whatever is there on the right hand side, right side of this diagonal element. Okay, the third element. So that operations we keep on doing until we get such a format. Now once we get such a format, what we do is called as back substitution. Why it is called as back substitution is because now once I get this form of equation, and also I'll be having x1 up to xn is equal to, we will be having b1 up to bn, and this will be also modified anyway, so I'll put just a dash here. Okay, so what will happen is that you can clearly see 0 into x1 plus 0 into x2 plus so on 0 into xn minus 1 plus something, okay, 0 plus 0 plus, okay, something something plus, okay, the last element which I'll call say something z into xn will be equal to bn dash. Okay, now you can clearly see, because since we've had come up with the zeros, everything became zero here. Okay, so I need not worry about this. So directly I can here calculate it as xn is equal to bn dash divided by zn. So this is called as back substitution. Now if you come to the last but one row, what you will get is, say I will say p into x n minus 1. Okay, all the preceding elements they will become 0 0 0. Okay, p into x minus 1 plus q into say xn will be equal to bn minus 1 dash. Now you already have calculated xn, you know q, you know bn dash, and you know p. So you calculate xn minus 1. So that is why it is called as backward substitution, because you are going from xn to x1. Okay, so that's the procedure which you follow generally in Gauss elimination. But again, the Gauss elimination, again, it has several problems, especially when the size of the matrix becomes very large, the number of operations also becomes very large, and really it becomes unfeasible for a computer to do all these calculations. Okay, that's the whole issue there, and I have never kind of used this Gauss elimination in my CFD routines anyways. Okay, and never do I use the direct matrix inverse also. And then you have similarly you have decomposition of this A matrix into L and U matrix. Okay, so that's called as LU decomposition. So you have A into X is equal to B. So you decompose the matrix A into a combination of lower triangular and upper triangular matrix. That is why it is called as LU decomposition. Okay, so L into U is equal to B. Now I have clearly told that once you get this upper triangular matrix here, you can solve the elements, you can solve these values. Okay, so for example, L into, let me take it as, say for example, U into X. I will take it as some D, value of D, okay, is equal to B. Okay, now I will try to get the value of D. Okay, this you know, this is again very easy. You get a lower triangular matrix, again multiplied by some values of t, you have to find the values of t, right? So here you do forward substitution, you cannot do backward, because here you have all elements 0 in the first row, you will get directly the first element, so that is called forward substitution. In that way you find d. Now once you find d, it becomes this system again, it becomes what do you say, upper triangular into x is equal to d. So here now you can again follow the same backward substitution, find x. So that is your LU decomposition. Okay. But the thing is, the challenging thing is to find L and U. Okay. Again, when the matrix size becomes very high, finding the values of L and U is very costly. Okay. You can do this operation. These are very easy. Okay. Once you find L and U, it becomes very easy to do forward substitution and then the backward substitution to ultimately find x. So that does not take computational resources, but finding L and U, it takes a lot of operations, and then we run into computational cost problem. Okay, so usually I haven't seen this technique also to be used much in the CFD field. Okay, I personally haven't seen much. Okay, and then you have a very good algorithm, I would say, okay, which we can nicely use it. Okay, that is called as your Thomas algorithm or the tridiagonal matrix algorithm. Okay, so this is very much applicable, very much ideally very perfectly applicable for your 1D equations, okay, for your one dimensional equations. And you might feel that one dimensional equation, what is there, they are not really used. Okay, we are always in the 3D world, 3D equations are used. But let me tell you that in some of the industries also I have seen that for in some cases 1D equations are also used, 1D governing equations, to solve the industrially challenging problems. Okay, people usually sell that industrial problems, they are not your 1D or 2D, they are 3D. But what happens in many cases is that industry people know how to put their resources in a proper way. So when they know that, okay, in the second and third direction I do not, they will be having variation, but it's not much as compared to variation in the third direction, and the third direction variation is what they are really interested in. Okay, and they know that it will not affect much. The first and second dimensions will not affect the third dimensions much. People solve 1D equations only. And in our blood flow in arteries also, when the interest is on pressure, when we want to find what is the pressure variation and not the flow velocity variation, people use 1D models to solve the pressure value at different points in the arterial networks, and there have been many papers also in that regard. Okay, so just I want to highlight the point that, okay, it's not a very basic thing. Okay, 1D equations are also used. Okay, and for 1D equations, to solve 1D equations, this is one of the very good method. Okay, this tridiagonal matrix algorithm. Now, tridiagonal matrix algorithm, why it is suitable for 1D is because when you solve 1D, you have only three elements, as I said. You have like AP into TP plus AE into TE. Sorry, this should be capital E plus AW into capital TW. Okay, so you have only three elements in the matrix, three elements in a row of a matrix. Okay, and that is why it is called as tri-diagonal. It is diagonal and there are three elements tri. Okay, 1 2 3, other elements are all 0 0 0. Okay, now in similarly, so this is for row 1, and again third element will also be not there, as I said. Only AP and AE will be there, AW will not be there for first row because it will go into boundary conditions. Okay, so similarly for second row you will get AW, AP and AE. Okay, all are 0. Now using the technique of Gauss elimination only, you will try to come up with a simplified form of this equation, wherein it becomes an upper triangular matrix. But even with upper triangular, many elements are 0. Okay, even in the upper triangular form. Okay, only this whatever is there, AP and AE dash will be there, they will get transformed. Okay, because of your Gauss elimination. And AW dash, AW will not come, that is what I am telling. It will be only upper triangular, all the elements will become 0, that is transformation will do. And very good formula is already available on the in the literature. You can use directly that formula. Okay, just to directly get the values of these xn values. Okay, so that's the advantage of using tridiagonal matrix algorithm. Are there any queries till this point? These are the direct methods which I was discussing. If yes, please let me know on the chat box. Otherwise, we can go with the indirect methods. Okay, so these were some of the direct methods. Uh, as I told, direct methods, you do certain set of mathematical formulations, you get exact solution for the values of x there. Okay, now usually in many of the cases, as I told, this is applicable only for 1D, 2D and 3D you cannot apply this TDMA. Okay, now can do modifications and then apply it, but directly it is not applicable. Now when you go to really complex systems, 2D and 3D, and when if the equations are coupled, that is the point there. You do not get a sparse matrix. That is basically when the many of the elements are zero, call it a sparse matrix. You do not end up with sparse matrices, and at that point of time these all these direct methods do not work properly. I mean, they at least they take too much computational time and all. Okay, so at that point of time you have to go with something called as iterative methods. They are also called as indirect methods, but I would say iterative methods because that has a more meaning. Okay, here. So as I told, direct you kind of get in the exact solutions there. That we can call it as direct methods. Okay, but in iterative methods, uh, we try to do a trial and error kind of thing. Okay, you already know what is trial and error. We try with some value, fit in the function, see whether it is fitting in properly. If it is fitting in, go, that's the solution. If it is not fitting in, try to improve your guess. Okay, so improving the guesses successively till we get a correct result. That's the whole game in this iterative method. So we take an initial guess of the temperature values or any flow variables, and then we substitute in the equations. Okay, we substitute them in the equations, and then try to update the further values. Okay, like for example, if I have 3x plus 2y is equal to 4, and then if I have 5x plus 10y, okay, is equal to 16. Now I have an initial guess for x and y, right? Now I try to calculate the value of x using the initial guess of y, because it has to fit in both of these equations, right? So using the initial guess of x, y, I try to find x. Okay, I get some x value, new x value, which is different from old x value. Now again I substitute in the second equation, and I know that this equation also needs to be satisfied. Now calculate the y value, second value. Okay, now I will again get a new value for y. Okay, now again check whether the difference between that old value and that new value of y, whatever you have got, if it is coming out same. And also that is not the only point. It should also, you should also just casually see whether these equations are being satisfied or not. That is also very important. Okay, so that also you have to check, but usually when you get difference to be very small, these are satisfied. Okay, so till then you have to just go on repeating these steps. Okay, so that's the whole procedure which we do in iterative method. So there are mainly two iterative methods, Gauss Seidel and Jacobi. So in Jacobi what happens is that, so when I calculate this x value using y value, I take the previous iteration only, zero iteration value of y only to calculate x, and then when I calculate y, still I use zeroth iteration value of x only to calculate y. So this is one round of iteration. This we call it iteration 1. Now similarly we go to iteration 2, wherein we take the x and y values of iteration 1 only. Okay, so that is your Jacobi method. But whereas in Gauss Seidel method, as I told, once I calculated this value of x, okay, using this first equation, I substitute this value of x only directly in the second equation instead of taking the value from previous iteration, zeroth iteration, for calculating y at first iteration. I take the value of x at the first iteration only. Okay, this is computationally more easy actually, if you see. Okay, this is more the Gauss seidel is computationally more easier to do. You need not store something as t old, okay, and take t old everywhere. You just play around, like you write t only everywhere, okay. So that ensures the correctness of Gauss seidel. And through our previous tutorials, we have seen how to implement a Gauss seidel without actually learning what is Gauss seidel, okay. So that is as easy as that, okay. Without knowing also, we were trying to write down, push it, okay. So that is very easy to understand, easy to write the code also, okay. So now these are the two methods, okay. And then I think in the final lecture, I think we saw what is the preconditioning also, and this is a slightly advanced stuff, okay. So till the iterative and direct methods, we are quite clear about that. But as I told you that some of the matrices might be very stiff. Why I call stiff is they have many elements in that row, okay. And what we usually call some matrices as well conditioned, and some matrices we call it as ill conditioned, okay. So that also you have learnt in the class. So what happens when we change the coefficients of an ill conditioned matrix? If we change even by 1%, the results, the x values, change by 100%, okay. So that is called as an ill conditioned matrix. Whereas in a well conditioned matrix, even by changing only 1%, the results change only by 1%, okay. So that's the nature of well conditioned matrix, okay. Gauss seidel, can you brief a bit? Okay, just I'll explain it again. So mainly, let me take a equation for temperature only. Okay, so now you have, like, for example, this 1D conduction only, okay. I have T1 to Tn, okay. I have intermediate points T2 up to Tn minus 1 or something like this. Now I have an equation for these things, okay. So for example, I have like T1 plus 2 T2, okay. T1 I know, okay. Let me call it as T0 and Tn plus 1, just for simplicity. T1 plus 2 T2 plus T3 is equal to 0. I have this equation. Now similarly for the third grid point, this is for second grid point, I had this, okay. For the third grid point, I can have like something like T2 plus 2 T3 plus T1, okay. It should be all in terms of this whatever temperatures are there here, T1 plus 2 T2. So let us change the coefficients for 3 T3 is equal to, say, some value, say you can have something like 8, something like that, okay. Now similarly I will have third equation. So again, T1 plus 3 T3 plus 4 T3, sorry, this should be T2, is equal to 10. Now you might say that for the third node or for fourth node, T1 will not come, okay. So usually what we have is, like for example, if we have n internal grid points, okay, then we will have n equations also, okay. So we might not have T1 and we will have T4, okay. But even then we will have those many equations also into the picture, coming into the picture, okay. So here I have like, basically what I am trying to tell is that I have three equations and I have three unknowns, okay. So that is a solvable set of equations. In CFD also you will have like n plus 1 internal grid points and you will have n plus 1 equations, okay. Now what we do is that we assume values at the initial guess, at the initial level, okay, at initial iteration 0, let me call it as, okay. And that can be 0 also, okay. It's not a problem. If you don't know, you can put it 0 also. I will have T1 at iteration 0 is equal to T2 at iteration 0 is equal to T3 at iteration 0 is equal to 0, okay. Now I come to the first iteration, okay. I try to solve the value of T1 at the first iteration. Now what I do is that I will write T1 is equal to minus 2 T2 minus T3, But what I have to do, I can take only the zeroth iteration values. Okay, that is how I calculate the value of T1 at first iteration using T2 and T3. Now similarly I will use this equation, the second equation which I have written, to calculate T2 at the first iteration. But here I'll take T1 at the first whatever I have calculated earlier, because I already know T1, right? I already know the value of T1 at first iteration. Okay, and then the remaining it as it is, minus 3. T2 is already taken into our picture, 3 into T3, right? T3 at zeroth iteration, because I do not know the value of T3, that is why I took it as 0. So whatever we know, basically we will take at that current iteration only. Whatever we don't know, we will take it as previous iteration. Okay, this will just speed up the process. In Jacobi method, what we do is we put everything in terms of T0 only at T1, and at T2 everything we put it as at T1 iteration 1. Okay, that is the main difference there. Okay, and then similarly we calculate T3 using the third equation, but here we put T2 and T1 both at first iteration because we know both the values. Okay, so that is how we try to find out T1, T2 and T3 at first iteration. Now we go on to second iteration. Okay, and then we do the same thing. T1 at second iteration will be 2 minus 2 into T1 at first iteration. This also again at first iteration. Okay, and similarly we calculate T2 at second iteration, okay, and T3 at second iteration. Now we compare the values between the second iteration and the first iteration, T1 at second iteration and T1 at first iteration. Are they close enough? Are they less than, say, 10 raised to minus 6, some residual which we specify tolerance? If they are less, then that's the solution. Okay, otherwise we usually go to again next iteration. Okay, so does that answer your question, Ayas? Did you understand the working? Yes, sir. So in the code it is very easy. Okay, in the code what happens is that it becomes very easy. Like T of ij. Okay, let me take just 1D. T of I is equal to, you just write minus AW of TW, that is I minus 1. Okay, and minus AE TI plus 1 divided by AP. This is the whole step for I is equal to 1 to n. Okay, you have a1 aw of you should have the it stored it as like a matrix. Okay, aw of 1, ae of 1, aw of 2, ae of 2, something like that. Okay, so for I is equal to 1 to n, I just calculate this ti, and I then after coming out of this loop I check it with the previous iteration, that I will store it as t old anyways. So t minus t old, I will check whether it is less than epsilon or not. If it is less than epsilon, I will break the loop. Okay, so that's very easy to implement in a program. Okay, this Gauss seidel, that is why I have been always telling that this is usually what is followed. Okay, this implementing these direct methods are difficult, and they you run into problems also in some of the cases, especially when you implement this direct methods. So that's all about the direct and indirect, and I was just talking about I think the preconditioning also. When you have an ill-conditioned matrix wherein the results change by just 1% change in the coefficients, you get 100% change in the results. Okay, those are called as ill conditioned, and there is a proper way also, because you do not know the results. How do you know, how will you know that 1% change will cause 100% change? That you cannot understand because you don't know the values of x, right? That is what you are ultimately trying to find out. Okay, so there is a way in which we see check whether the matrix is well conditioned or ill conditioned. So that is using your condition number. Okay, in the weekly content also, I don't know, I did not see like a threshold value wherein you say whether the matrix is ill conditioned or whether the matrix is well conditioned. So usually what I have seen in the literature and what I have referred to is usually a value of less than 10 or better would be 1. We call it as well conditioned below that values, and above those values 10 or something like that, we usually call the matrix to be not well conditioned, and we try to condition it well by using the preconditioning. Okay, so these are a bit advanced stuffs, and although I call them advanced stuff, these are usually used in your commercial softwares. Okay, and a very famous method, I mean, people do not use this Gauss seidel or something like that in your commercial softwares. So usually you have conjugate gradient methodology to solve the linear system of equations. That is much more faster method, actually, the conjugate gradient method. So you try to make this as a you try to convert this as a quadratic equation, and then once you draw this curve, whenever you reach this minimum function of this function, you have the slope to be 0. You try to jump from this point directly to this point and then directly to this point. That is usually we do it in conjugate gradient method, and sometimes these conjugate gradient methods are used in a CFD solver, typical CFD solver, wherein the equations are too much coupled and all. Okay, so those are mainly the last parts of this weekly content. Okay, so with that, let me just start with the questions for this week, and once we are done with the questions, I'll try to show a code wherein I have implemented the tridiagonal matrix algorithm for your 1D unsteady state heat conduction. Okay, so that you understand how to write the code for these methods, and then we can wrap up. Okay, so yeah, so the first question, hang on. While programming, okay, we need to store zeros in the lower triangular and upper triangular matrix in LU decomposition method. Is it true or is it false? Can you write down on the chat box? Okay, Siva has written it is false. Why is it false, Siva? Can you unmute and say? I think I have allowed the microphone access. Oh, you don't have mic. Okay, you can write maybe why it is false. Because in L and U matrix you have zeros, right? In lower triangular and in upper triangular matrix, which is what we find in LU decomposition, which I had just now explained also. Typically there are zeros. Okay, I mean, zeros are there in the lower triangular and upper triangular, but I just want to know what made you say that the answer is false. Okay, the question is like while programming. Okay, while programming. Okay, I thought only zeros to be stored in L. Okay, you are telling that in U we need not store zeros. Only in L we have to store zeros. Is that true? You are telling only in L I have to store zeros. In U you need not store zeros. Is that what you are telling? Okay, just let me clarify. Uh, while programming, the question is while programming. Okay, anyway, you might be right and I might not be getting your point here. Okay, so while programming we need to store zeros in L and U matrix. Okay, so typically your L and U matrix run something like this. Okay, so there are zeros in L and U matrix, which you see here, like L corresponds to lower triangular and U corresponds to upper triangular. You decompose the matrix. I have explained the procedure also in the recap of this video. Okay, so typically we have zeros, but the thing is while programming we try to think about the memory constraints also. So what happens is that matrices are 2D arrays and they take up a lot of space as compared to a 1D array. Okay, as compared to 1D arrays they take up too much of space. So although you can do it like this is not a issue, this is not a problem, but what typically people do is that they try to convert this into 1D arrays. Why? Because there are many zeros here. Okay, we don't want to really store them. Okay, so the L matrix is stored something like this. Okay, all the row 1, row 2, row 3 elements are stored first, and then your row 2, row 3. Okay, because row 1 in the second column becomes 0. Okay, you end up with one less space here. Okay, in this 1D array. Okay, and then L33 lastly. Okay, this is how we can store it, and we can operate with this kind of L matrix also. And similarly we do that in the upper triangular matrix also. Okay, and in upper triangular, this is not u33, actually this should be also 1. Even we don't store this diagonal elements also, because we know that it is 1. Why do I want that? Okay, usually I store only the 3 elements. So you can now clearly see that I am reducing a lot of size of the matrix. Okay, and these matrices do occupy your RAM space also in your computation, during computation. So people try to avoid this, and they have come up with an optimized way to kind of store this. Okay, so the answer was correct actually. The answer should be false. We need not store zeros in L and U, although there are zeros in L and U. Okay, so usually it's the way optimized way of calculating L and U matrix. Okay, so the answer is false for this. Okay, now the second question is as follows. Arrange in proper sequence the steps for LU decomposition. This I have explained it. Okay, just now. What are the steps which are involved in LU decomposition method? One, for a given A, find L and U such that A is equal to LU. Second, take assume that Y is equal to UX. Okay, and so basically we have to calculate, what do you say, solve the system for Y. Okay, Ly is equal to, it will become B, because Ux we have taken it as, this Ux we take it as B, and then solve it for Y, and then solve the triangular system. Ux is equal to Y. So what should be the correct order here? Can you write down on the chat box? Okay, I think whatever they have given itself is, I think, correct. Okay, so typically we take, first we decompose the A matrix into L and U. Okay, such that A is equal to LU, lower triangular and upper triangular. Okay, that is what I have written here. Then what become, what the system of equation gets transformed into A, we write it as LU and X as it is. So LUX is equal to B. Okay, now the thing is, we try to find a system, say L into D is equal to B. Okay, D, that they have given it as Y here. Okay, I think, yeah, L into D I have written that D should be Y here. Okay, so L into Y, we solve for B. Now we can easily find uh, Y, right? That is what I had told earlier, using the forward substitution, because this is a lower triangular matrix. Okay, now once we get D, it becomes very easy. Now what is D? It is U into X. So U into X is equal to D. U is upper triangular, so we use backward substitution. Okay, then find X. Okay, so then that is what the order of sequence it has been given here. So A is the correct answer. Yes. Okay, so I hope you have understood this. Okay, if there are any queries, please let me know on the chat box. Okay. Okay. Order of the decomposed matrices in LU decomposition for a given matrix of order n cross n. So A is of order n cross n. So they are asking what is the order of L and what is the order of U as a matrix. Okay, they have written specifically matrix. So what should be the answer? Yeah, it should be the same, right? I mean, it's still in the matrix form. We have not done it, converted into 1D array or something. So it's in a matrix form. They will be of the same order still. Okay, so they will be also of the order n cross n and n cross n only. Okay, so B should be the correct answer as you have rightly written on the chat box. Okay, so the question number 4 is on the preconditioning technique. Okay, and they have mainly introduced a technique. I'll just explain this also to some extent. Multi-grid technique is also classified as one preconditioner. Is it true or is it false? What should be the answer? Okay, so do you know about the multi-grid technique, Ayaz? You can unmute and speak maybe. You can unmute yourself and then maybe let me know whether you know multi-grid technique or not. Am I audible? Okay, okay, fine. So let me otherwise explain. Okay, so actually it's a what do you say, acceleration technique to solve the equation. So usually these system of linear equations take time to solve. Okay, to get the answers in an iterative method they take some time. So what we do in multi-grid technique, as the name itself indicates, multi-grid. Okay, so we have a domain which we divided into many number of elements using a particular grid. Okay, we generate a particular grid and divide the domain into small number of control volumes. Okay, so now we do the same procedure multiple times so that we get multiple grid. So one of them is coarse and one of them is fine. Okay, so if I just take a two level multi-grid, one of them can take coarse and one of them I can take it as fine. Okay, now the actual results I want on fine grid only, because I want accuracy. Okay, that I can get using only fine grid. Now but initial guess I have to make na. So initial guess I make it using a coarser grid. Okay, there is always some residual which remains because it is a coarse grid. Okay, then I try to only solve for that residual. Okay, so that's the main fundamental idea of this using multi-grid. So what happens is that now I get a much faster convergence in the fine grid. Okay, because I have a very good solution which is not accurate, but I have a good solution which I get it using the coarse grid. Okay, so that accelerates the convergence procedure in my fine grid. Okay, so that's the main technique. So as I told, there are two grids which are involved. Now, for example, if I want to just solve a Laplacian equation, I kind of convert this into expression of Tij. Dx square means actually it's nothing but Ti plus 1 here. Okay, Tij plus some delta values. Okay, delta x, something like that I have written. Okay, now you can write this as a function of Tij only, and then I divide the Tij into Tij course. Okay, plus some residual. The actual result will be whatever I get on Tij plus some delta t, that is the residual, which because in course grid I cannot find the correct answer. Okay, that's the whole point here. So basically I am splitting up the matrices here. What is happening is that uh, if you try to relate it with the preconditioning, so you have Ax is equal to B system, but what I am trying to do is I am trying to introduce the coefficients from the coarser grid, so that I am splitting up that matrix particularly. It is an indirect way, but in that way it acts as a preconditioner. Okay, so you might have learned about the Gauss preconditioning in that particular preconditioning section. So this also technique acts as that kind of a preconditioning wherein you split up the matrices. Okay, and that is why multi-grid technique is also classified as one of the preconditioning technique, although it was not brought in as a preconditioner, but it acts as a preconditioner uh, in a way by splitting up this whole matrix. Now you can write L of Tij plus L of delta Tij is equal to 0. So in that way it is a preconditioning technique, but it was not introduced to be a preconditioning technique. It was just to kind of accelerate the our convergence of the solution. Okay, so yeah, so that is why it is classified as preconditioning techniques. Is this clear? Okay. Now the question number 5 is, for a well conditioned system, small change in the coefficient of matrix A or on the RHS matrix B will lead to only small change in the solution vector. So I have already discussed this. The definition of well conditioned matrix I have already discussed that. Okay, what should be the answer? True. Yeah. So the answer should be true. That's the definition of well conditioned matrix. Anyways. Okay. Huh. So a matrix it is, a matrix. A matrix is solved by LU decomposition as A is equal to LU. Then in the below given option, what should be the value of U? Okay. So there is a standard procedure for finding the values of U. Anyways, okay, that you might have discussed in the weekly content. So that is one approach through which you can calculate the value of U. And if this was not an MCQ question, then you would have had to go through that procedure. Okay. So basically, let me just take a new board. Is equal to, this is the matrix A that you decompose it into L and U, right? So basically in the L matrix you have L11 0 0, L22 0, L33 0, and you have L21, L31, L32, and then you also have here 1 U, what do you say, 1 2 U13. Here diagonal you have 1, here you have zeros, that's the upper triangular, and you have U23. Now you can see that A is equal to L11 into 1. So you get L directly here. L11 is equal to A because you know already the elements of matrix A. And then what do you have? L11 into 1, that is one thing. L11 into U12, you get it as B. Okay. Now you know L11, you calculate U12. Okay. Now what is the value of C? C is equal to basically your what do you say, U13. Okay. So that is how you kind of find out the answers. Okay. It is because L11 into U13 you will get it as. So B value you will get it as L11 into U12. Okay. Now similarly C value you will get it as L11 into U13, right? U13 plus 0 into something, 0 into 1. Okay. So that will be anyway 0. So you will get this type of equation. Now what will happen? L11 you have already calculated it to be A. L11 you know, you calculate L13 L12 and L13, okay, using this L11. So that is the way in which you calculate the values of u in a systematic way, and you can generalize this and come up with an algorithm also. That's a different point, but this is the understanding for the way in which we calculate L and u. Okay, but if you see this particular options, that is not required, because in these options only option number one is upper triangular matrix, and they have asked u matrix. Okay, so directly you can guess it here that it should be option number A. Okay, but if it was a descriptive type of question, you would have to solve it in the way in which I just explained it. Okay, if that is understood. Okay, now let us go to the next question, question number 7. Okay, so for this system of equations, 4a minus b minus c is equal to 3, and second equation, third equation. So calculate the values of a, b and c after first iteration using Gauss Seidel method. Okay, Gauss Seidel method I have just now explained it. Okay, first you have to take an initial guess, which is given as 0 0 0 here. Okay, once you take an initial guess, first you calculate a. Okay, then you calculate b using the second equation, but a you have to take from the first iteration only, whatever you have calculated previously. Okay, similarly you can calculate c from the third equation, but take the values of a and b from the first iteration. Okay, so that's the procedure. In general, you can, I think, work it out. Okay, diagonal is not one, diagonal need not be one. You are solving it using Gauss Seidel method, no? You have to just see whether I think it is diagonally dominant or not, which I think it is. Okay. So in the previous problem, you're telling me, just wait a second. Ah, sorry. Yeah, you are right. Yeah. I don't know whether I missed a option or what. I don't know. Maybe there was another option also, I think. Yeah. You needs to have one across the uh, diagonal. Yeah, I think so. I think there was one more option which I kind of missed out. Or yeah, thanks for pointing that out. Okay, yeah, this is, all the three are not correct. Actually now I remember, in this question all the four were not correct actually. Yeah, now I remember. Yes, by mistake I put this at last. Anyway, the fourth option also did not have, I mean, one in this diagonal. But anyways, this any of the options were not correct. Yeah, now I remember. Yeah, thanks for pointing that out, Shiva. Okay. Yeah. Coming to this question. Okay. Using the values of okay, using the values of initial value, using the initial values of a, b, and c as 0. Let us try to see how we can calculate the values of next iteration. Values for next iteration. Okay. So in the first iteration, so what we can directly do is we can take 3 plus b plus c divided by 4. Okay, so it will become b of 0 and c of 0, because we do not know b and c values at the uh, first iteration. Na? So we usually take it from the previous iteration. Okay, so it will turn out to be 3 by 4. Now when we are calculating the b value using this second equation, we usually take the a value from this first iteration only. So that is what I have done here. Now if you see, c I have taken it as 0th iteration only, but a I already know from the first iteration. I directly put the value of a from the first iteration. So it will become, basically c is 0, it will not stay. 3 plus, it will become 3 by 2 and divided by 6. Okay, it will become 3 by 4. Now when we calculate c from the first iteration, okay, I take A and B from the first iteration, which I already know. So this is the main difference which exists between Gauss Seidel and Jacobi. I hope at least by now you people might be very clear. Okay. In Jacobi we always put, even while calculating C of 1, I put A of 0 and B of 0. I always take from previous iteration. Whereas for this Gauss Seidel, whatever is known at that iteration, I usually take that. If it is not known, only then I'll take it from the previous iteration, like I took C from 0 and A from 1. That's the whole difference. Okay, so these calculations you can do anyways, so it will come out to be 3 by 2. Okay, so then the correct answer should be 3 by 4, 3 by 4 and 3 by 2, which is the option number D. Okay, yeah, so this is the way in which we calculate. Any queries regarding this? Okay, so let us move to the next question. In this was also just an extension of that, using in the second iteration what we get. That is also you can do in a similar way. Again, you can see that when I am calculating B at second iteration, I take A at second iteration, but I take C at first iteration because I do not know C value at second iteration. So which I don't know, I take it as previous iteration. Okay, so this is the way. The ninth question, this is as follows: the direct method to solve the system of equation. Which of the following are the direct methods? So that's the question. So what should be the correct answer for this? Gauss elimination, Gauss Seidel, Jacobi, successive over relaxation. I think I did not highlight upon successive over relaxation. I think I explained only Gauss Seidel and Jacobi. But this successive over relaxation or successive under relaxation, that is also just an extension of your Gauss Seidel and Jacobi method. Okay, so just let me explain that also, because that is also an important thing to understand. Okay, so we usually get the values at different iteration, right? So now for example I got it as second iteration. Okay, now I have a ti at first iteration also. Okay, now I have completed two iterations, I'll be moving to the third iteration. Okay, now what usually happens is that when there is a very kind of steep increase in this iteration values, we might actually miss the original values. Okay, if the variation is like this, something like this, and the correct value is somewhere here, and we might go from one iteration at this point to second iteration, we might go here only direct. Okay, we might miss this point in very rigid kind of equations. So for very rigid kind of equations, we typically do under relaxation. Okay, and in very relaxed systems, we do over relaxation also. That is for a good, that is for uh, speeder convergence. Okay, faster convergence. Okay, that is for that is we do over relaxation there. But in under relaxation, just let me explain. What we do is Ti at 2, I change it. I have got some value, but I do it over. I do under relaxation with respect to Ti from the first iteration. Okay. So usually what I write is W into Ti, whatever I calculated at second iteration, plus 1 minus W into Ti at first iteration. Now if I was at third iteration, I would write 3 3 and here 2. Okay, I hope you understand that. So if I put W value to be 1, what it will happen? T2 Ti at 2 is equal to Ti at 2 only, it will become. Okay, that is nothing. But when I keep the value below 1, say for example 0.7, so what it will do is, say for example I have this value as say 4, and if I have this value as 2, now the updated value of Ti at second iteration, that will become something like, say for example if I have W is equal to 0.5, so it will become 0.5 into 4 plus 0.5 into 2, so that will become 2 plus 1, that will become 3. Okay, you will come somewhere in between 2 and 4. You will not directly jump to 4. Okay, so this is called as under relaxation. Okay, yeah, Siva, you had any doubt in practice assignment you are having? We are not allowed to actually solve your actual assignment in this tutorials. Okay, but I will just check it. I have actually not checked your actual assignment because we are not allowed to solve those questions. Okay, but anyways, if you find it not correct, you can discuss on that course forum, okay, and we will be there to kind of answer that. If there is some issue, that will be corrected, and if you try to tell that to NPTEL, they might put grace marks also. I don't know, but if your argument is correct, okay, you are telling Q3 answer is given as D, and you are telling that the answer should be A. Okay, you can put up this on the forum, and you can contact the NPTEL also. Usually, I have seen such things. They happened last year also, and this NPTEL people, they had given some grace marks later on, if there was something like that. Okay, you can contact them. Practice assignment. Okay. Because we were given mainly the access to your previous year course, so I do not have the access to your current year's course. So can you just discuss the question? What was that question? Because I did not have access to that. I am not enrolled to your course actually. So okay, I'll see it. Okay, maybe I can enroll to the course also, and I can see, uh, and then just randomly just check what is that question. Okay, I'll just let you know in the next week maybe. But if you definitely feel that whatever answer was given there was not right, you can just uh, write a mail to NPTEL team also. Okay, they'll get back to you. Last year also I had seen such problems to be happening. Some wrong answers were given, and then they kind of gave grace marks or something like that. Okay, you can just contact them and let them know. Okay. Okay, fine. So, huh? No, I'm not able to see. Oh, sorry. I did not scroll down. Sorry. Okay. It's only for practice. Okay, fine. Under relaxation parameter is used to accelerate the solution. No, over relaxation is used to accelerate the solution. Uh, to reduce the memory required per iteration. No, it doesn't reduce any memory. I don't think so. Select proper method to solve. Select proper method to solve the equations. I don't think so. So I think D should be the answer. It doesn't accelerate the solution anyways. Only over relaxation will accelerate your solution. Under relaxation will not accelerate the solution. Or actually, under relaxation will make your solution to converge slower. It will take more time under relaxation when you do. Okay, it will be the reverse. Okay, I think D only should be correct. Memory anyway you don't reduce. Okay. 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 Fine. Huh. Huh. Finite difference using polynomial. What do you want to say? Huh. maybe I have to see, but the general trend is like what you are telling. I think is we try to fit an equation and we try to find a b c values for some polynomial function. Like at x is equal to 0, I have some value. At x equal to delta x, I know some value, and x equal to 2 delta x also I know some value, right? So you are trying to see in this case, I think you are trying to fit a equation using 3 point stencils, right? Like something like that. You know the number of points in your stencil, and you know whether you are coming up with a forward difference or backward difference or central difference. Okay, you know that, right? And you know when you kind of come up with like say for example df by dx, okay, you know how many stencils will be involved, right? This much information you will be knowing, right? So basically, I had told you, I think when I was discussing, like usually what happens is that if we have like two stencil points here, df by dx, okay, if we have like fi plus 1 involvement of f of I plus 1 and I for forward difference, and for backward difference I minus 1 and I, usually it is 2 point stencils, and the order of accuracy will be one less than the number of stencil points, okay, so it will be order of delta x only, okay. Now if we have 3 stencil, it will be delta x square. Now this is applicable for forward difference and backward difference, whereas for central difference, if we have say for example 2 stencils, then it will be order of delta x square. The number of stencils is equal to the order of accuracy for central difference. For forward and backward, it will be one less, the number of stencils. You should see the number of points in the stencil. In second derivative, the things will change again. That is what. If you have, like, for example, the number of stencils to be 3, okay, so then you will get a second order accurate scheme, okay. So using, I think, central difference, okay. So again, forward and backward difference will be one order less, so it will be 1. So with the 3 point stencils, you will get first order this thing accurate scheme with a forward or backward, whereas with the central difference, you will get second order accurate solution. So it will go on decreasing. So for example, when you go on to the what do you say, this is for d square f by dx square. Now if I say d triple dash f by dx cube, okay. So then what will happen is, if you have 4 points in the stencils, you will get third order accurate, okay, for sorry, you will get second order accurate for a central difference, and you will get first order accurate for forward or backward difference. So it will go on reducing like this. You understood, na? So you have to always stick up with the you were saying something. So basically it goes on reducing, and you have to see with central difference first, and then with forward and forward and backward difference, it will be one order less than that, okay. So now I am telling that with central difference, like for example f dash, you will have 2, you will have 2 order of accuracy. Now f double dash, you will have 3 points, and you will have order of accuracy to be 2. Now here it will be 4 points stencils, and the order of accuracy will be 2, okay. Now this is for central difference. For forward or for backward difference, it will be one less. So with 4 point stencils, you will have only first order accuracy. Here with 2 points, you will have one order of accuracy. This is for f triple dash, okay, f triple dash, okay. It will change like this. So this you can understand for central difference. So once you understand for central difference, you just calculate for forward and backward using the number of stencils points. Yeah, the number of terms minus 1, that is true for central difference. That is what I am telling. So for example, if you have fi plus 1 minus 2 fi, okay, plus fi minus 1 divided by delta x square, that is for f double dash. This is a second order accurate, but you have 3 point stencils, na? You have 3 point stencils, but it is second order accurate. With 3 point stencils, you will get only first order accurate for forward or backward. This whatever I have written, that is for central difference. For first forward or backward, it will be one less with the same stencil. Did you understand this? No, three terms. If you have more than three, if you have six terms, then the order of accuracy it will become four. Basically, in central difference, it always goes by 2, 4, 6 order of accuracy. Huh. You understood, na? Huh. So for backward and forward, you will have to always do one minus. You have to start from one particular point. Okay. So this is the starting point with 3 point stencils. Okay. You will get first order of accuracy. With 4 point stencils, you will get now what second order accuracy. With 5 point stencils, you will get third order of accuracy. So with like that, you have to go on. Okay. But usually I don't think you will get up so many points. Usually I think 3 or 4 points you will get. So you have to determine based on that 3 or 4 points, whatever you get, how many stencils are there. Based on that, I think you can determine the order of accuracy. But I don't know, there might be other way also. This is what I mean, I have seen because I usually try to determine the order of accuracy sometimes just by looking at the equation, how many stencils are there, and then try to look at that. But there might be a more formal procedure also. I mean, which we do in Taylor series truncation error, which we see the leading order term of the truncation error. But in polynomial, I think you will be directly having these things already. The exact the stencil points you'll be having. So that is why I thought this might be a more correct approach. Hmm. 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 Yeah. 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 Correct. Yeah. Hmm. 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 248. Yeah. Hmm. 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 Yeah, yeah, for central difference, yeah. This you, yeah, yeah, continue. Yeah, yeah. You cannot generalize like that number of stencils minus 2. It keeps changing with f dash, f double dash, f triple dash. That is why this that is applicable, like whatever minus 2 you are telling, that is applicable for this f or double dash here. So yeah, yeah. Hmm. Hmm. Yeah, yeah. Okay. Fine. So, but there might be some more method also. I don't know. Based on whatever I know, I told. Maybe I'll see if there is some more concrete way in which we can try to get the truncation error or something like that. I don't know. I'll just see. but we usually try to do this guessing work using this number of stencils. Okay, anyways, uh, yeah. So yeah, so just let me skip this question. These are like based theoretical questions only mostly, which are based on our discussion. So I just wanted to just show a code. Okay, this slides anyways I'll be uploading. So mostly you have theoretical questions only ahead, and this is calculating the condition number, which you know, which you are already there in the weekly content, and then this is the question on Gauss elimination. How do we do Gauss elimination? Just by doing the row manipulations. Okay, so this anyways are there in your weekly content also, you can just directly see them. Okay, so I just want to show a simple execution of a code for a tridiagonal matrix algorithm with which we can wrap up today's session. Okay, so mainly the equation, I think my laptop is hanging. Okay, so the equation which we will be trying to solve, as I said earlier also, that is a simple 1D unsteady state heat conduction. So we have a temporal term and we have a conduction part also, rho square T by 2x square. Now, as I said, we will be trying to solve it using implicit time stepping, not an explicit. Explicit, we have already done this in the previous tutorial sessions. Okay, so Tn plus 1 minus Tn is equal to alpha delta T by delta x square. Okay, into Ti plus 1 at n plus 1, because this is implicit time stepping. Okay, that is what I had told, minus 2 Ti. So this is again a second order accurate finite difference which I am doing here. Okay, Ti plus 1 at n plus 1. This is also at n plus 1. Okay, so this is how we kind of discretize it. This is minus Tn. I hope this is you are, this is readable. Okay, so what will happen now is that using this we will form the equation. The equations will look, this is at I, okay. So the equations will look something like this, minus, now alpha delta T by delta x square, let me take it as one term, say D, something like that. So minus D into Ti minus 1, okay, plus 1 plus 2D, okay, because I have 1 coming from this term, 1 plus 2 into D, okay, into Ti, plus uh, this Ti minus 1, it will have again negative, minus T into Ti minus 1 is equal to Ti at n. This will go on the right hand side, this term. Okay, it is going on the right hand side. Plus, I don't have anything. If volumetric heat generation is there, I'll get some Q triple dash also. Okay, okay, into delta T. This will be Q triple dash to delta T, because delta T I have just put it on the right hand side. Okay, and these are all at n plus 1. So I have to solve this. You can clearly see that there will be only three terms in the matrix, in the row of a matrix. Okay, so that will be your A term. If you arrange this as A, B, C in a matrix, your A term will be D minus D. C term will also be minus D. B term will be 1 plus 2D. Okay, so this you can directly solve using tridiagonal matrix algorithm, and that is what we will be trying to see today. Okay, so we will just take a simple case like with heat conduction and without heat conduction. With heat generation and without heat generation. We will take some 100 and 0 temperatures at the left and right hand. The only thing which you have to be quite careful here is that when you form this A matrix, you should not take the boundary grid points into account. I mean, you should not take them as a row. Okay, so basically when you determine the A, it should be usually the order of A. If you have say n points, 1 to n points, you should the order of A, that should be n minus 2 cross n minus 2. Okay, so the two boundary points are not included in this A matrix. Okay, in that way you have to calculate the A matrix. Now when you come to the second grid point, which acts like a first row, okay, I'll write second grid point, but it is the first row of this A matrix. So you usually put the AW on the right hand side, because I minus 1 Ti minus 1 will be T1, right? It will be 100, you already know that. So here we put it on the right hand side, so we directly start with BC, whereas in third and like till n minus 3 it will go on similarly. Okay, now this A value will come here, so B plus D into T1. Okay, this is only for the first row in the B matrix. Okay, similarly when we go to n minus 2, n minus 1, sorry, this is 2 to n minus 1, so it will be the number of elements will be n minus 2. So in the last one also you will put te, this is I plus 1 na? So this you will put it, because you know tn, so when you come to n minus 1 you put it the right hand side, b into tn. So this here you will be calculating T2 to Tn minus 1. Okay, so that is what I wrote, 2 to n minus 1. T2 to Tn minus 1. But when you calculate T2, you need T1. T1 is already a boundary, so that I'll put it on the right hand B matrix. Okay, and similarly A will not come. So similarly here also C will not come. C is associated with what? Your I plus 1. So it should be the other way around actually. C is this D, anyway it will be same. C and A is minus D. C and D, A are anyway same, only the B is 1 plus 2D. Okay, so here you'll get only A and B, will not get C. Okay, so this is how you have to arrange the A matrix. So this is what you have to know, the arrangement of A matrix and the RHS matrix. Okay, if that is known, then you can easily implement this code. So first, I hope you are able to see my code. My laptop is running a bit slow here, just hang on. So first I have kind of defined what are the values of length of the straight one dimensional domain. This is like, you can think of it like a straight 1D rod or something like that. Straight 1D beam. Rod would not be good to take, because just consider it as like a one dimensional beam. And then length is 1, so alpha is a thermal diffusivity, your k by rho into Cp, that is alpha value, that is equal to k by rho Cp. Okay, that is what I have written here, that is thermal diffusivity alpha. Now del t, I can take anything because I am doing implicit time marching here, and then del x I have taken it as zero point 0.1 because I just take 10 elements. Okay, you can actually take n is equal to 10 and then write del x is equal to say L by n, that also you can do. And I am just trying to solve it using a finite difference. I am not doing finite volume and all here. That is also one thing which I want to tell. Okay, I want to just show the implementation of implicit time stepping here. That's the main agenda using TDMA. And T left and T right are the boundary condition, and Q volumetric, let me just first set it to 0. Okay, and then an important thing is, as I said, boundary conditions and the initial conditions. So the initial conditions I have given T of 1 and T of nx as T left and right, others are 0. That's my initial guess. Okay, you can take anything, but simply I'll take 0 as the initial guess, and then I am setting up the matrix elements. Okay, so as I told you, this I think I deleted it. Okay, so that your A and C will be equal, they will be actually minus of alpha delta t by delta x square. I substitute it below, and then B I have taken 1 plus 2a. It is actually, you can write it like something like this also, D is equal to alpha into delta t by delta x square. Okay, then A is equal to D only, and B is equal to 1 plus 2D, and C is also equal to D. Okay, this is actually minus, but minus I have taken it here actually. So in general, what will be there when you define the A matrix? A of I comma I minus 1, that is your A element A, that is A W. So I have put minus here, that is because you got minus alpha delta t by delta x square, so that is why minus here, minus A. And similarly AE is A of I comma I plus 1, that is minus C. Okay, now A of I comma I is the diagonal element, which is your B element, so that is why I have put B. Now B you can see is nothing but 1 plus 2D. Okay, so that's the thing, that is normal internal how you define the values of this matrix A. Now when you come to I is equal to 1, that is the first row, as I told, it corresponds to the second grid point, and here you do not want to take I minus 1. I mean, it becomes unphysical also, because you don't get 0 index in a MATLAB. Okay, so you cannot take I of I minus 1, so that you have to put that, anyways you have to put it on the right hand side. Only I of I and I of I plus 1 I define, that is the normal way, B and minus C. And when I come to nx minus 2, and I have defined here that A is size is nx minus 2 nx minus 2, so I cannot go to nx minus 1, I cannot put I plus 1, so only I minus 1 and I define it as A and B. I plus 1 I cannot do, I will put it at RHS. So I enter the times stepping loop here first, as I said. Then what I do is that I have to calculate the values of finally temperature. Okay, by solving this equation, A into T is equal to B. So I have to set up this A, which I have already done. B I call it as RHS matrix, and this will mainly involve T I at n. Okay, it will involve Ti at n, plus at the first row and at the second row it will involve that your A element, I think, and it will involve C element. Okay, only in this is only for first row and last row, whereas for all the other rows it will involve T1 T2 up to Tn at the nth previous time value. Okay, so this is your RHS matrix. Okay, now that is what I have defined it here, t old of 2 to nx minus 1. Okay, and then okay, otherwise it is 0 in the internal points. If it is at the corners, I have defined it as A into t left, A into t right. Okay, and if you have a volumetric generation, again that also comes in the right hand side of the matrix system. Now once you do this, this is all, that's what you have to do. And then Thomas algorithm, you need not remember or do anything. There are already routines which are available in the MATLAB. You can just go through the net and then just copy paste that algorithms for solving A and B system. Okay, usually they write TDMA of A comma B. B I have written it as RHS here. Anyway, once you do that, we have to check for convergence. uh, Whatever is the temperature we have got using the Thomas algorithm minus the T volt. Okay, so that is the convergence to step out of this loop. Okay, so that is what. Now the important thing is tridiagonal matrix algorithm. As I told, you need not write a code for tridiagonal matrix algorithm. Actually, your task is to only set up these matrices. This matrix algorithm I have directly got it from a online resource. Okay, you can write it, you know the derivation, you know the values and all that you can do, but just this is to save the time. Okay, once you set up the values of A and B, it has the routines through which it can calculate x, the function x, that is the output which you find, uh, TDMA of A comma B. It will do the your backward substitution on the changed matrix. First you have ABC in every row, then it will get just converted into an upper triangular matrix, and that too with many elements as 0. Only you will get B dash C dash B dash C dash B dash C dash. Ultimately in the last row you will get only B dash, and that B dash into X will be equal to your D dash on the right hand side, RHS dash, whatever it is. So then you will directly calculate X of n to be just the RHS of n divided by C of n. Okay, this is transformed things. Okay, these are because that transformations are done here. So this is how it works, but anyway you can get this directly without any You need not write this ideally. Okay, so that is what it will solve. Okay, now when I run this code, it will just plot the temperature values. Okay, you should expect a linear variation of temperature from the left and right hand, because we have not put any heat generation source or something like that. Okay, so I don't know, it is coming up with some error. Undefined. Okay, nt of length t. I did not require this. So first I wanted to stop it at some time, so I had written this nt is equal to length of t function. So I wanted to stop it at some t, specified t, but later on I changed it, so that is why it's not required. So it will stop when the convergence is reached actually. So when this error goes beyond below 10 raised to 6, it will come out of the loop. Okay, so anyway, I think it'll take some time to run this because my laptop is also running slow. So are there any queries regarding today's session? If there are, you can unmute and can ask the question. You can contact me on mail. Okay, Anthony, maybe I'll share it there. Okay, my mail id. Okay, my mail id I'll share you. My mail id I'll write down on the chat box. Can we use the other norms for calculating condition number? What norm you want to use? Not get. As far as I know, we usually use the row sum norm. If you are getting the same value, then I think it should be correct only. But I personally do not know whether you can use some other norms or what. Just check if you have some idea regarding other norms. If you are getting the same answer with as that of by using row sum norm for different matrices, then I think it should be correct. I don't know, but in general, I do not have any idea of whether there exist some other norms or what. Okay, you are getting different values, then I don't think that should be correct. But even if you are getting different values, if the trend at least is same or what, that you have to see. Like using the row sum norm, uh, if you are getting low value, and if you are getting through some other norm, if you are getting very high value, then that norm is not correct as far as my information goes. Okay, but I personally, as of now, I do not know whether you can use other norms or not. I'll have to see. Okay. Any other queries? Okay, so this is your temperature variation, which is the linear variation. Now, if I just add some volumetric heat generation, the temperature will actually move out of the boundary temperature values. Okay, so you are supplying some heat, so it is a non-linear variation here. Now, instead of the straight graph, at the center you get a higher heat, higher temperature, which you have seen in the analytical solutions also, I think. Okay, so this is the way in which you write the code. Now you can take any time step. This is unconditionally stable algorithm. Okay, that's the advantage. I am using implicit time stepping here. Okay, if there are no further queries, okay, thank you for attending. So next week is the last week. So we will try to solve Navier-Stokes equation using some method. I have not thought about it, but definitely the next session I think will be mostly on coding only, and that too for Navier-Stokes equation. Okay. Okay. So we'll see, that will be the final part for lid driven cavity, and let us try to see what are the general things which we can take forward from this course in the next week. Okay, and what will be the future steps for you apart from writing exam. Okay, how you can go forward in this CFD career. Okay, so yeah, thanks for attending. If you do not have any queries, you can leave the meeting. Okay.